Good morning, Unit 3 for Physical Education students, and I'm sure you're very excited to be getting to the next part of Area Study 2, Energy Systems, Fuels, and the very important term, Energy System Interplay. Let's get straight into it. Okay, we're going to refer straight back to our key knowledge points. Again, remember this is on the VCAR website, and it should also be in the front of your summary booklets. So we are looking at the characteristics and interplay of the three energy systems. When you release some keywords you would have heard many times before, so I'm going to let you read those in your own time. We're looking at the fuels and how we power our body. We're looking at the chemical fuels and of course the food fuels which we eat. And then of course we need to look at the relative contribution of the different energy systems used in different activities in regards to the intensity, the duration and the type. Because there's so much amazing content in this key knowledge, I'm going to split this up today into two separate recordings, so you get to hear twice as much as of my voice, which is very, very exciting. Okay, some key skills, again, straight off the VCAR website. We're going to be doing a bit of data collection, a few lab exercises, energy system interplay, looking at that sort of stuff, and of course the different types of recovery, which is best suited to bring about optimal performance when we are talking about which energy system's been utilised or depleted. All right, little graph here again breaks it up to our three specific energy systems that we talk about: the ATP-PC or CP system, the anaerobic glycolysis system. We don't call it lactic acid anymore, so never use that again. And our aerobic system, and then of course you can see how we use fuels, and you can see that they're all responsible for the movement that occurs. All right, now this is a good thing. All of the three energy systems are all working to do the same or achieve the same thing. The way that our body is powered for movement is by the breaking of the adenosine triphosphate molecule. So these are high energy bonds, phosphate bonds just here. We need to break one of those phosphate molecules off. That then produces the energy for our body to move. And of course, the quicker we can break these off and rebuild them, the higher the intensity we can maintain. But there's a lot of limiting factors on this, which we will get to in the next couple of minutes. Okay, a little bit of an introduction here. The energy released from the breakdown or metabolism of food is not able to be transferred directly to the cells to be used for biological work. We can capture this energy in a form that can be used by the body, and that is ATP. So ATP can only be stored within the body in limited amounts, very small amounts, 2 seconds of maximal effort, and then you've ATP is depleted. So of course, for all of your daily tasks, we need to be able to continually rebuild that ATP. And we know most things are going to last longer than a couple of seconds. So your body all the time is continually resynthesizing or replenishing ATP, or rebuilding as we call it. Okay, some very important keywords here. Interplay, often a definition or a term that's poorly understood. So the key thing, whenever you see the word energy system interplay, you need to say at the commencement of activity, all three energy systems work together. So that's what interplay is. However, we always know that one of those out of those three is going to be the dominant energy system. So, but the other two are switched on, but one will be more dominant than the other. And we know that that's totally dependent on intensity, duration, and the availability of oxygen, which we'll get to in a slide coming up. We have two anaerobic systems, so that means these systems can function without oxygen. That's all anaerobic means. Put it in your summary books. We've got the ATP-PC system, short, explosive, and the anaerobic glycolysis system, again, used to be called the lactic acid system, but we cross that out now. We don't call it that anymore, so don't ever use it. We know that's a byproduct of the system, but it gets confusing. Okay, and our aerobic system, which means it can resynthesize ATP with oxygen. And this here explains the energy system interplay, and the key thing is here it's at maximal intensity. So if you're doing a team sport and you're stopping and starting, this is not what the graph would look like, because during those little breaks and the whistles, your body systems have a chance to replenish some of those stores of ATP, PC. So then of course we're going to see difference with that interplay. But imagine you've taken off as fast as you can, there's a lion chasing you, and you've got to run for 4 hours. This is what an average interplay would look like. So at the commencement, down here, they're all switched on. The ATP PC system is going to be dominant for that first 0 to 10 seconds, although the anaerobic system is contributing as well from the start, as is the aerobic glycolysis system. And then as our stores of ATP and PC are depleted, the anaerobic system comes in, and that's going to be the thing that's rebuilding or resynthesizing that ATP to enable a high intensity exercise to continue. And then of course the aerobic system is also slowly starting, and sort of the studies suggest at the moment that at this point here it's about 60 seconds. So it's 60 seconds. The contribution of aerobic and anaerobic glycolysis is 50-50. Now this other little fancy word here, you might want to learn that one. Aerobic lipolysis is once we are starting to sort of run out of our CHO, our carbohydrates, then fats will take over, and you can sort of use those for quite a while. So a really good graph. You'll see that again. All energy system interplay. Okay, so some of this stuff I've already gone over. Just imagine each energy system is like the gears of a car, or 3 different types of cars, and one of them's really fast, one of them's not as fast, and one of them's slow and can go forever. So this is sort of the way that we can perform. So in this way we use a gear that is appropriate to the needs of the activity. So of course, if you're going at a nice steady intensity, you're not going to be using your ATP PC system because it's fast and explosive. But if you wanted to throw something or jump as high as you could or sprint for a few seconds, then that's going to be the most readily or the quickest system to fire away. All activities require energy contribution. Again, coming back to that interplay, there are always going to be at least 2 of our 3 systems sort of contributing. However, only one system is predominant, and that's again coming back to that same definition of interplay. These 3 words here are crucial whenever we're asking you what is a system is dominant. There's the bell. Don't go anywhere yet. We need to talk about how hard you're going, how long do you need to last, the type of exercise you're doing, and of course it also comes back to the availability of oxygen. Okay, fueling performance. We need to fuel our daily physical activities, and of course the fuel is what we use to rebuild the ATP stores and keep performing at a certain intensity that we desire. So you can see the fuels here: creatine phosphate or phosphocreatine, carbohydrates is a beauty, lipids or fat, and in extreme situations your body can use protein, which is not very good for your body. Okay, skipping through here, the bell's just gone. Okay, the first fuel here, CP, the most important fuel for those very short bursts. It's very simple chemical reaction, and it rebuilds the ATP very quickly. However, it's only stored in small amounts, so once it's depleted, we need to sort of have a bit of a rest in order to replenish our PC stores. So it's a positive and negative each one. Carbohydrates, this is the body's preferred fuel during regular physical activity. It can last, it kicks in quite early on and lasts for a couple of hours, generally about 2 hours without carbohydrate loading. It's very versatile because we can use it with or without oxygen, and I'll talk to you a bit later about the side effects of breaking down carbohydrates without oxygen. We're going to build up some byproducts. It's also stored in a number of places around the body, so we're going to show you a table, and we talk about the glycogen and the glucose and where that's stored and how it's transported. Glucose in the blood, glycogen in the muscles and liver. So it is actually ready to go in the muscles, which can also mean why it's so quick. So that's sort of what we're looking at there. And this is probably the key to show you the difference between our aerobic and anaerobic glycolysis system. They're the same steps. We start with glycogen, goes to glucose. We break down and resynthesize ATP. We get pyruvic acid. So this guy here is producing these byproducts. So carbon dioxide, breathe it out, no worries. H2O, water, bit of sweat, no worries. We've had enough oxygen to add a few extra chemical reactions, which means that these are non-harmful byproducts. Okay, this anaerobic guy, we're in a bit of a rush with the lion still chasing us. We have run out of our PC stores. We need to replenish quickly or resynthesize the ATP quickly. So we break down the glycogen, and we're basically missing a couple of steps. So instead of producing these nice products at the end here, we end up with lactic acid, and this is a combination of lactate and hydrogen ions. This is going to be stuff that you go over in class, but very important. Hydrogen ion here is the bad guy that we're going to talk about later, but again, we're talking about a metabolic byproduct. So the side effect of breaking down or resynthesizing ATP using carbohydrates without oxygen is that particular byproduct. Okay, then we go to fats. Again, a very important fuel for submaximal activity and also in regular sitting around the place. Fats are going to be fantastic for that. A lot of people can store fat, again, around their bloodstream, and also we can store the excess stuff as adipose tissue, which can, in some cases, slow an athlete down because they don't want to be carrying too much extra weight, but it could be, for those longer efforts, quite important. Protein's sort of like our emergency store when we're in a sort of a famine, or you haven't eaten for 2 weeks, or something like that. Your body will actually break down protein, which is your amino acids, your muscle stored around your body. Of course, it requires a heap of oxygen, and of course, it means that you're going to have long-term damage to your muscles. Okay, so what's the difference between the two? Intensity. Fats aren't going to work as well as carbohydrates at higher intensities. Carbohydrates are the preferred fuel above sort of 65% of your max VO2. It can basically use half as much oxygen as fats, so it's a more efficient fuel, so it's more economical, as I've just written there. Fats require twice the amount of oxygen, and they're longer, slower process to break down. However, the fats will give you a greater total amount, or greater yield, which is a nice word that we use there, to continue to resynthesize that ATP. Another graph here showing you that breakdown. Again, you can see the pathway the same with the carbohydrates, glycolysis pyruvate. When we have the oxygen here, aerobic, that's all good. Anaerobic, we get these bad guys here. And then again, the reason the aerobic pathway is slower is because there's extra steps involved around the Krebs cycle and a few different bits. All right. It's good to know on this little table here, guys, a few examples of where you're going to get some different food fuels from. Again, keep it simple. That's just a guide. Nothing to worry about there. And the last little slide of this part 1 is if you're going to go for a bit of a run tonight after school, and you go, look, I'm going to run for 6 hours. I'm feeling pretty good. Your body's going to start off. You've got some good carbohydrate stores. It's going to start using that. And after about between 2 and 3 hours, it's going to have what's called the changeover point. This is provided that you're not constantly eating carbohydrates during that first 2.5 hours, and then fats will take over as the main fuel. And you can see there that as the time progresses, fats will go up and the carbs will go down. So that's a nice graph there, and that is going to finish us up. So stay tuned for part 2, where we're going to look at specific energy systems and some more key terms. So keep up the good work.